Okay, so we are going to now start D2, and this deals with stellar characteristic and stellar evolution. Okay, so let us start here with the first topic that we have. So we have the first topic as stellar spectra. What exactly is stellar spectra? You know, we have already studied about your emission spectrum and absorption spectrum. And absorption spectrum. Now in a star what happens? Stellar means star. In a star what happens? If you imagine here, this is a star and this is your outer layer with hydrogen, which is undergoing fusion, which is very hot, okay, and inside temperature is much lower, and sometimes we call it photosphere. Okay, now this is a cooler zone. Now if we are watching from here, if this is our eye, let's say, then we will be able to see a continuous spectrum here. So what do I mean by continuous spectrum? Is something like, say, you can see maybe, you know, yellow color here, and then you can see maybe another color, and then maybe another color, so when you see one after the other colors, this is known as your continuous spectrum, right? This is called your continuous spectrum that we get example from sun. How do we get? We get in the form of VibGR, for example. This example, okay? Now, let's say this is yellow, and from the cooler zone, one photon comes out. So this is a photon coming out, from cooler zone, okay? Now this photon which comes out as an yellow. So I will draw with a yellow here, okay? Is coming yellow here. Because this is yellow and this is also yellow, it gets absorbed and it comes like a dark line. So it comes as if, so the incoming yellow from light, from photon of cooler zone is absorbed, okay, is absorbed, and that we see as we see as dark line. That is your absorption spectra. Absorption spectra. Okay. So, hence, now let us go back again. By receiving these absorption spectra lines, we study properties of a star. Okay, we try to find out what is happening inside the star, and that's very crucial thing for us. Okay, and that can only be done with your absorption spectra, because that only helps us. So this is known as your stellar spectra. So spectra, or the absorption spectrum that we observe from the stars. Remember, outer layer is very hot, inner is cool. Outer layer always gives us continuous spectrum, whereas the inner layer gives you always the line spectrum. Okay, and then it gets absorbed here, and then you watch and then you judge what is the property of this star, specific star. Now note, there is an important thing to note here. Note is that as stars have high temperature, there will be less absorption spectrum or absorption spectra. Sun is much cooler compared to a star named Vega. Sun has approximately 5800 Kelvin, while Vega has 9600 Kelvin. So Vega will show less absorption spectra as chances of cooler spots are less. Okay, now for our easy use, because stars emit different light, so there is a name given to each one of these. They have been classified. So we have technically classified stars. Okay, how have we classified stars? The bluest is named as class O class. Okay, bluish is named as B class. Okay, similarly, if I go down, the red, the least energy, is labeled as M class. So maybe you can refer online to see more class of stars. Okay, now that's about the stars, the stellar spectra and the class of stars, because we receive certain colors, so we from the absorption spectra. This is from absorption spectra. Remember that this is from absorption spectra, and the light that we receive from absorption spectra, we have given a name for them. Okay, just classified them into groups. If you recall from earlier unit 7, we studied something called Wien's displacement law. In 8, I think, yeah, in the energy chapter. Displacement law. Just going to recall that once more, where Wien had plotted a graph between intensity and wavelength. So, for example, I have Vega here, okay, which is at 9600 Kelvin. How much was that? Let us just check once up. Which was 9600 Kelvin. So, Kelvin. Then we also have our Sun, which is at 5800 Kelvin. Okay, Sun. And if you look at both of these, you can see that lambda of the Vega and lambda of the Sun. So wavelength of Sun is greater than wavelength of Vega. Okay. Now Vega has higher peak intensity compared to Sun. That may be because it is much hotter. Okay, and then we also know, we have seen that wavelength is inversely proportional to temperature. Why? Because energy is directly proportional to temperature, but energy is inversely proportional to wavelength. Okay, so lambda is inversely proportional to temperature. Therefore, lambda into T has to be a constant, and that constant was named as Wien's constant. So the formula became lambda into T equal to 2.9 into 10 power minus 3 millikelvin. So this is given in data booklet. Okay, this is in data booklet. Now let's proceed ahead. Next topic we have is something interesting, and this is called your special star, a sort of star which is called as Cepheid variable. Okay, star which is called as Cepheid variable. Now Cepheid technically means fluctuating. Okay, now question is, what is fluctuating? It means it undergoes a change in intensity. But good thing is that we can predict this change in the star. Okay, so Cepheid variables have a fluctuating nature. Fluctuating what? Is a fluctuating intensity. So it undergoes a change in intensity, but good thing is that we can predict this change in the star. So we know that, you know, the Cepheid star will have this sort of change, which means they have a specific cycle of intensity. Okay, let's see little more on this aspect. What do we mean by specific cycle of intensity? So if I have to draw this, I have to draw a graph between luminosity and time. And if you see, the graph goes, okay, 1 second, I think there's some problem here. I'll just erase that because, yeah. Okay, so it climbs up again. So here there is an increase and here there is a decrease of what? Of luminosity. Look at the graph. The increase and decrease is not a sine graph, is not a sine graph. The time taken by star to brighten up is less. See, it's very less. So if you look at here, and if you look at this time t1, and if you look at this one as your t2, you will see that your t1 is less than t2. Yeah, that's very interesting characteristic of the Cepheid variables. So there are some Cepheid variables that have been identified already and that are available in our Milky Way galaxy. And they are very interesting stars to study because their luminosity keeps on fluctuating, and that has become a, it has developed a curiosity. This behavior or this nature has developed a curiosity in astrophysicists. Okay. Now we will go ahead with the next topic. We are going to study something very interesting here, and that is known as Hertzsprung-Russell diagram. Okay, which is also known as HR diagram. Okay, so what does Hertzsprung-Russell diagram tell us? This is very important for us because it actually explains you a lot of things. Now, Hertzsprung in his graph has kept the temperature increasing in this way. Okay, so it increases this way. Keep this in mind. This is very important for us. Here he has kept luminosity. But the luminosity is kept as a ratio. Luminosity of the star by luminosity of the sun. Okay. Now he has fixed here some belts. The first belt that we keep here is like this. This belt is called your main sequence. So star spends initial time in this stage no, is something like we use the word childhood. Yeah. So all the stars, they spend that time here, and let's say our sun is somewhere here. We will keep the sun positioned here. So this is the sun. Temperature is approximately 5800 Kelvin. I'm keeping. Okay. Now there are certain things here aspect. A star which is in a range of approximately 1.4 times the mass of the sun. So let's say they all become something called your red giant. Okay, this is called your red giant. Red giant. The supermassive stars, which are very huge stars, okay, huge stars, they become your something called super red giant. Super red giant. Now super red giant are very massive. That's too massive. Because they are very massive, they are very massive. Because of this, gravity contracts the star, and these stars land up in becoming two things. They can either become a neutron star, or they can become a black hole. Okay, and we all know that black hole has a very infinite gravity. So it has a infinite gravity. Now coming back to our red giant, the super red giant, after a long time, they tend to become something called white dwarf. White dwarf. So our sun will also become a white dwarf. Okay, so sun can become this, and anybody within that range of 1.4 times mass of sun will become a red giant, and then they will come to a stage of white dwarf. Do not draw this line, dotted line, through this main sequence. It is not allowed. Okay, because you cannot pass through the main sequence, so you have to show it above the main sequence. Now once you are in the white dwarf, and then the white dwarf star will after some time explode and then become a supernova, and from supernova you will again get a nebula. Okay, nebula. So that's how it happens. Now we will write one by one each one of them to understand what exactly they are. So first, main sequence. Just wait, I don't like this color. I'll take this one. Yeah. So main sequence. Newly born stars having fusion reaction has sufficient hydrogen to carry out the reaction. Okay. Now coming to the next one. Second, red giant. These are cooler compared to sun, they emit less energy, fusion reaction has decreased, has reduced. Interesting thing is, if you go up, their luminosity has become higher. And they have higher luminosity. That's a very interesting thing to think, huh? Why? City. Okay. Third are super red giant. You know, these are technically stars which emit almost 10 power 5 times more energy than sun. So which means they are massive. But their temperature is about same as red giant. However, they have greater luminosity. Greater luminosity. What does it mean? It means they are more brighter. Okay. They are technically more brighter. So they are more brighter. The fourth is white dwarf. So when fusion is over, the core is hot, and that increases the temperature, but their luminosity decreases. Our sun will end as white dwarf, and there was a scientist who is known as Chandrasekhar. So we have something called Chandrasekhar limit, which is also having another name, where he says that star with mass about 1.4 times the sun will become a white dwarf. Okay, that's a limit he gave. So there was a limit he has put. That's why it's called Chandrasekhar limit. Okay. Now, you have to do some self-study here. You can also think and research. Okay, you can think and research more on little bit on black hole, neutron star, and something called Oppenheimer-Volkoff limit. I mean, this limit is linked with probability of star to be a black hole. Okay. Now, coming to your next part, that is the mass luminosity relation. And this relation states that the luminosity is directly proportional to your mass power 3.5. So as mass increases, luminosity also increases. Okay. Now, I think we have almost finished this unit also. There is nothing much here now. So, technically, this is the end of both. So, what we have exactly studied here, if you look here, is that starting from here, okay. So, we understood the stellar characteristic and the stellar evolution. So, characteristic involves your emission absorption spectra. We have learned how in a single star, the outer layers, which are hot, emit a continuous spectrum, whereas the inner ones, which are cooler, emit a line spectrum, and that can be seen as an absorption spectrum. And once you know the absorption spectrum colors, you can label them. Sometimes you see blue, sometimes you see red, it can be yellow, so you have a label name for them. And this shift of the color that you watch is linked with energy here. So Wind displacement law can be used here to study that property, as we discussed for Vega and Sun. And then we saw Cepheid variable, which are also a set of stars which have a very critical property. The property is that its luminosity keeps fluctuating. But interesting thing is the fluctuation is not very uniform. So the curve is not sine. You see, the increase, it happens in a very less time compared to the decrease. Right? That's a very interesting thing to note here. And then we saw the Hertzsprung-Russell diagram, where Hertzsprung has given us a set of diagrams, and we can use this diagram to locate the position or the fate of a star, how it's going to actually end. There are some more additions one can make here. It can be like you can have here something called your Cepheids. Okay, the Cepheids normally are found in this zone here. So if you look at the diagram, main components are your main sequence, your red giant, super red giant, and the white dwarf. Okay. So technically, if you see, then you will understand that the white dwarf, okay, the white dwarf explodes, becomes supernova, which is again the dust, the gas particle, and from there again nebula is formed. and that's a new star again. So you see, this is the whole life cycle of a star actually. So from white dwarf it explodes and it becomes supernova, nebula, and again it starts. So all this happens because there are some gravitational actions, there are some decrease in the pressures, so the temperature starts changing and all this stuff happens. Hope this is clear.